everybody in this class, I encourage you, it's not in your best interest to get an incomplete in Physics 141. Physics 141 is a stepping stone to more physics, right? So you shouldn't hold yourself back. Make sure you get through the class. Doesn't, it's more important to go on to do more physics than to be looking at the same stuff again, right? So I encourage everybody to turn in something for 4 labs so that we don't have incompletes in the class. It's not good it holds people back and makes them do less well. Actually, you want people to move on. You don't actually need to know 100% of what's in 141. You need to know some fraction of it, its foundation, right? So I encourage everybody to get the 4 labs in for this class. Yeah. And don't be strangers next year, next term too. Hopefully we'll all be back on campus a lot more and without covering, so I'll actually be able to see people. Okay, so what are we talking about today? So I'm going to start off by talking about trajectories on PV plots. So what's the setting? The setting is we've got some kind of thing, it's a gas system. And we're going to keep the number of particles in it fixed. So N is fixed. I'm not going to worry about things like phase transitions, but the energy can change. The temperature might change. The volume might change. And we showed that this was true. PV. So this is heat. So a change in energy is a heat, and this is work. So this is heat, and this is work. This is the heat. So the energy and change in energy in our system S is the heat that flows into it, plus the work that's done on it. So, so now what we're going to do is talk about take a parcel of gas and compress it, or let it expand, let it exchange heat with a thermal bath that's at one temperature, and then exchange heat with another thermal bath that's another temperature. Those things give you these little loops in PV space. They also give you loops in TS space if you want in temperature entropy space. And if it's periodic, then it's like an engine. And so things like heat engines, air conditioners, refrigerators, and those kinds of things you can think of them as little trajectories in PV space, where you have these periodic cycles, and each part of the cycle is either exchanging heat or you're doing work on the gas, or the gas is doing work on the surroundings, or both. So that's what we're going to talk about today. So I just wanted to remind you of that, because that's essentially what we're going to be using for all the operations. And again, the setting is we're not letting the amount of stuff in the system change, the amount of molecules. We're not going to talk about other things like phase transitions or anything. So, so let's be specific about signs. So the work done by the gas W, so it's PdV, but if I integrate it around a path, so if I have some path, here's P, and this is V, and I start here and I move to here, then in each piece of this path I can look at PdV. And then the work, so this is done by the gas. If I was doing the work on the gas, there would be a minus PdV there. So I can integrate this up along the path. And that gives me the total work done on the path. So yeah, okay. So now what are these? We need some definitions. So reversible. Okay, so what do people mean by reversible? So that usually means it's done slowly. And when something's done slowly, that means it's nearly in equilibrium. So it stays approximately in equilibrium. So by equilibrium, it means the total, so entropy, this means that entropy of the system plus your reservoir or your external, whatever is external to it, is fixed. So when you stay in equilibrium, you're staying at this maximum entropy state, so you're not, and if you're, you should, for the whole system, everything's in equilibrium, so the whole system doesn't change in entropy. So that's what's meant by reversible. And so there's a bunch of operations that aren't reversible. So like if you start off with if you start off with a vacuum and you put some gas in a corner and then you open up a spigot and you let the gas expand into a vacuum, entropy increases, but of the whole system. And that's not reversible because you actually increased entropy. So for many of the operations we're going to talk about, they're going to be done slow enough to be reversible so that we can use our thermodynamic relations on them. So there's a subtlety about this. Essentially, it means slowly, near equilibrium at all times. So isothermal. So that means constant temperature. So that's pretty easy to remember. For an ideal gas, remember PV is equal to NkBT, and energy, which I'll call U, is 3/2 kBT. So that's an ideal monatomic gas. This is time. So this for the whole gas, it would have an N if it's per particle without the N. So the total, if the temperature is constant and the number of particles is constant, then the total energy is constant. So this side stays constant. And that actually tells us that P is proportional to V to the -1 if you do let a gas change in volume or change in pressure. You have to, if you increase the pressure, you have to decrease the volume, right? Because you have to, if you want to keep it isothermal, which means you're keeping the energy fixed in the ideal gas, you have to keep this constant. So that's isothermal. So how about isochoric? So isochoric means a constant volume. V is constant. So volume, so that's volume. So remember W is PdV. So if V is fixed, that means W is equal to 0. So if I do an operation on some system that's a gas, and I make the volume be constant, then I'm not doing any work on it. But I could change its energy, but because du is q plus w, if w is 0, then du is q. And so isochoric operations mean that I'm just exchanging heat, and the amount of heat that's exchanged gives me the energy change. So these are, if I have a trajectory on a plot that keeps constant volume, then that's this du is equal to q for that operation. Okay, so that's isochoric. I guess I have a very small amount of room down here. Isobaric, that's pressure is constant. And if you do an operation on a gas with a constant pressure, then you are doing work because PdV is not 0. So the last two, I guess I'll erase some last two definitions that you'll see people use. We have well, let's do adiabatic. No, let's do isentropic. Isentropic. So this means constant entropy. So yeah, so you don't change the entropy. Adiabatic means without exchanging heat. So there's no heat exchange. And if you have an adiabatic reversible thing, usually it's isentropic. So adiabatic plus let me just spell that right. Adiabatic plus reversible usually means it's isentropic. Okay. So adiabatic is something that's often often happening. So there are many situations where you don't really exchange heat. So an example of that is actually if you compress a gas and it can't radiate, or it doesn't have a good way of no conductivity, it doesn't have conduction to something, so there's no way for it to get rid of energy, then that's an adiabatic setting. So actually sound waves are usually approximated as adiabatic because they're pressure waves in the gas, but the gas can't really radiate very efficiently while it's undergoing those pressure variations. So sound variations are considered, are usually approximated as adiabatic. Okay, so let's draw some pictures of operations. So here's one. If I have so I could put a little piston. Here's a piston. Draw the piston, and here's the top of the little plate here. And have my gases in here, in there. And suppose I start putting some weight on it, but I'm going to put weight on it really slowly. So the picture I've drawn here is you put sand on. So this is sand, and you just kind of slowly dribble sand on it. And so that there's a weight on it, so that it compresses. So, so supposing this whole thing is now sitting in some bath, like water at some temperature T. So that's a thermal reservoir, and I'm putting the sand on, so the gas inside here is being compressed. So I am doing work on it, but because it's exchanging, it's in thermal contact with this, water bath. The temperature is fixed, so the temperature of the gas will stay at temperature T. So the energy of the gas has to be fixed because it's staying at the same temperature. But I am doing work on it. So where's the energy going? Well, the energy has to go into the form of heat. And so there's heat. The gas would have heated up if I hadn't put it in this temperature bath. So there's a heat flow into the bath. And so the amount of, in fact, because the temperature is fixed, the amount of work done on the gas by compressing it all of it goes into the heat because it has to stay at the same energy. So that's an operation, and we'll take operations like this. So this is an operation where you're exchanging heat with some temperature bath. And you can build up, like it's either exchanging with hot or it's exchanging with cold. You have a heat flux into the hot reservoir, heat flux into the cold reservoir. In between those, you're doing compressions or expansions. Those are like refrigerators or heat engines or air conditioners. So these periodic cycling is made. So this is one of the types of operations. So why did I do this with sand? I did it slowly so it would be reversible. Otherwise, if I do it really fast, I could get an entropy increase. And then it wouldn't be, those relations are derived, assuming things stay in equilibrium. Okay, so that's one operation. So what if I don't have it in a bath? So it's not in contact with the reservoir. Now now I'm still compressing it. But in this case, because there's no, it's not in contact with the reservoir, there's no heat exchange. So Q is equal to 0. So no reservoir. So it's isolated. but I'm still compressing it, and that means du is equal to minus p dv, and I can integrate that out. Delta u is the integral of p dv, depends how you've compressed it. So this is actually, yeah, so the change, in this case, if you don't allow any heat exchange, you can compute the energy change in the gas. So if you're the beginning and the final volume, the beginning and final pressure, you can integrate that up and figure out what the energy change is in the gas. And then using the ideal gas law, you can get the temperature. So, so that's, if you compress the gas, it'll heat up, essentially. Okay, good. So, yeah, so now let's think about loops a little bit. So that's a picture of what physical setting you have. So this thing with a piston, you can kind of think of shuttling little bits of gas around and pressing them, compressing them. That's why refrigerators have compressors, and then letting them expand. So these little piston pictures, or it could just be an engine where you have an actual piston. So, all right, so now let's look at a PV plot. So it's V, and this is P. And suppose I start here, and this is P1, V1, like this. And then I go up like this, and this would be P2, and then I go over. So let's go along a trajectory. And then this, we're going to make this be V2. Then we're going to go down that way, and then we're going to go down that way. Okay. So here we have a bunch of paths. And so we're doing a little loop. So assuming we've got our little system and we're compressing it at constant volume here. So that would be heating it up. And then we're letting it expand, but keeping the pressure fixed. And then we're letting it cool off because the pressure is dropping, but the volume is staying fixed. And then we're compressing it at constant pressure. So these vertical paths, there's no change in volume. So no volume change. So du is equal to q. So those are easy. I mean, if you want to figure out the heat, you can figure that out. Whereas along these horizontal paths, you are doing work and there's heat. So what are the constant energy curves? So PV is constant at T constant. So, so P is proportional to V to the -1 at constant temperature. So those are curves like this. So it's inverse V curves. So things up here with higher pressure and bigger volumes are higher temperature. So you can think of these plots. U increasing U is in this direction, actually. So, so what happens if I go? So let's compute what happens if you go around a loop. Well, if you come back to the original position, then you've done no total energy change around the loop. But if I do what work, like, so what's the total work that's done around the loop? Well, I can compute, I don't do any work on the vertical trajectories, but on this one, the amount of work done by, so I'm going to do by the gas, so it's actually the integral of PdV. So the amount of work done on this trajectory is dV is delta, so this is P2 times delta V, which is P2 times, so I'm going in this direction, so it's V2 minus V1. So let's call this WA for this trajectory. No work done on these two, but I'm going, now what's the work done on this trajectory? WB, we'll call this one WB. And this is P1, and now it's V1 minus V2 because I'm going in that direction. And so the total work done around the complete loop is P 2 minus P1 times V2 minus V1, which is delta P times delta V. So that's the work done around the whole loop. And because I came back and I got the same energy as I started, the heat that's exerted going around this loop has to be the same as the work done going around the loop. So heat flow Q has to equal W because du is 0, delta U is 0 having gone around the loop. And so, so this will wind up helpful if you're trying to compute how much heat was transferred for how much work. So either you're trying, for a heat engine, either you're trying to do work to get heat transferred, like you're pressing on the gas to try and make some thing cold, like either your house or you're inside of your refrigerator, or you're doing work and you're trying to keep something warm, like you're trying to heat up your house and it's cold outside. Or you're using transfer from hot to cold to actually run an engine, like a car, something like that. So that means you want work. And so those are going to be related to the total heat that's being transferred in the loop. And because heat is involving changes in entropy, there are fundamental limits between the amount of work you can get out of something or that you need to put into something to give you heat transfer. So either whichever way you're trying to do things. So there'll be entropy related fundamental limits for efficiencies of heat engines or air conditioners. And that's where it comes from. Because if you think about these things as little loops in PDT space, the total work is total heat. So, okay, so that kind of gives you the backdrop for how these PV trajectories are used. So this is a trajectory in PV space, but we could do transfers and do it in TS space too. And you would get equivalently a loop in TS space too. You have to get back, always have to get back to the beginning for the whole system. Okay, so let's talk about some operations. So, adiabatic variations are very common. So I'm going to do that one special. Do it as a special case. So let's talk about the adiabatic variations of an ideal gas. And so what we're going to wind up with is we want to define something called the adiabatic index. So remember, adiabatic means no heat exchange. Okay, so no heat exchange. So no heat exchange. So that means du, which is the change in energy. So that would be TdS minus PdV, but because there's no heat exchange, it's just PdV. So, so if we have an ideal monotonic gas, then U is equal to 3/2 NkBT. And du so is just 3/2 NkBdt minus PdV. So this goes to that. So we also have the ideal gas law because we have an ideal. So this is monotonic. Monotonic. So that means single particles. That's what gives it the 3/2 comes from the fact that it's monotonic. If we had like a diatonic gas, we could have 5/2 or 7/2. So there's more degrees of freedom. This is from the degrees of freedom. This will become important later. Okay, so we also have the ideal gas law, which is PV is equal to N kBT. So I'm going to divide this side of the equation by N kBT, and I'm going to divide this side of the equation by PV. So N kBT, this will be 3/2 dt over T. I have PdV divided by PV, the P's cancel, and I get minus dV over V. So this I can, dt over T, I can write as a log, actually. D of ln T is equal to minus D of ln of V. It's just convenient. And this I can now integrate, actually. So let's put the power here. And I can move this minus sign there. And now I can integrate this. So I get ln of T to the 3/2 is equal to ln of V to the -1 plus a constant. And then I can take E to the whole thing, and I get T to the 3/2 is equal to V to the -1, and then this constant multiplies in, so I can just turn that into a proportionality sign. Did I make any mistakes? No, I didn't. Okay, good. So T, now I'm going to use the ideal gas again, and T is proportional to PV. So let's use that. So I have PV. Yeah, actually, before I do that, let's flip it over. So I'm going to multiply both sides by 2, take both sides to the 2/3 power. Let's do that. And I've got T is proportional to V to the -2/3. And now I'm going to use the ideal gas law. So PV is proportional to V to the -2/3. I move this to the other side, and I have PV to the 5/3 is a constant. Okay. Yay, that's what I wanted. So this whole thing, it wasn't like a very complicated calculation. What did we do? We used the degrees of freedom in the energy, and we used the ideal gas law. We used the fact that the change in energy was just from PVV work. And we found that if the change is adiabatic, meaning the change in energy is equal to only work, there's no heat, PV to the 5/3 is constant. So adiabatic variation in an ideal gas, ideal monotonic gas, gives PV to the 5/3 is a constant. Okay. So I promised I was going to tell you what the adiabatic index is. And that's this right here. So it's a power. So gamma is 5/3 is the adiabatic index. So it tells you, so temperature is not staying fixed for an adiabatic variation, but PV to some power is staying fixed. Yeah, so this was for a monotonic gas. And remember, we started with energy is 3/2 kT. So if we'd had more degrees of freedom, we would have gotten another adiabatic index. And so we had 3/2, and now we want to make this go to N over 2, where N is degrees of freedom. So if I redo that same calculation, then the adiabatic index, instead of being 5/2, it's 2 over N plus 1. And you can rewrite that as 2 plus N over N. And so for a molecule, you get 7/5 or 9/7, depending upon how many degrees of freedom. So for a diatonic gas, you'll get, instead of 5/3, you'll get something slightly different for the adiabatic index. And in the sound, so I mentioned that an example of adiabatic variations is sound waves. And so the sound speed actually is usually written like this, where it's the square of sound speed is square root of the adiabatic index of pressure divided by density. And so the adiabatic index actually comes right in there. And so you have to use some gas, you have to use like Euler's equations to find, and conservation of mass, and do perturbations to find the wave speed for sound waves. But and you do in the equation of state, which in this case you'll be assuming this is true for the sound speed, for the sound, variations in pressure and how they're related to density will give you that. That's why when you take derivatives of this for perturbations of some small pressure perturbations around a mean and density variations around the mean to solve for a wave equation, that's why the index winds up in there. So this is sound speed in a gas. Okay, so that gives you a derivation for where the adiabatic index comes from. Okay, so now let's go back to trajectories on PV plots. So we have V and P again, and so if we start in one place and we wind up in some other place, the total work done on the gas depends on the trajectory, right? So if I do something like this where P is 1 over V, so this P, so this will be P is proportional to V to the minus 1. This would be isothermal. But if I do, so adiabatic, and so adiabatic is P is proportional V to the minus gamma, because remember P to the gamma is constant for an adiabatic variation. So this type of, and usually this is steeper than that because 5/3 turns to 3/5. So this is adiabatic. I think that's true. So now, so depending upon how you do this, the work on one of these trajectories, I have to integrate up P dV. So we can now like derive some formulas for what's work if the trajectory is isothermal, or what's work if the trajectory is adiabatic. So let's do an isothermal compression. So if I start here and I wind up there, V, this would be V1 and this is V2, but I'm going to a smaller volume and a higher pressure, so that's compression. So if I go in this direction, it's compression. So let's do isothermal compression. W is going to be the integral of from P1, V1, it's PdV, and I'm integrating over volume, so V1 to V2, P V dV. So if it's isothermal, then it's, I've just used the ideal gas law, and so PV is equal to N kVt, which means P is N kVt over V, T over V, integral dV. And this is N kVt integral ln of V from V1 to V2, which is equal to N kVt ln of V2 minus ln of V1, which I can write as ln V2 over V1. Like that. And that's the answer. So, and in fact, you could write this as PV. Since it's isothermal, this is the same at the beginning and at the end. So I could write it as P1 V1 ln V2 over V1, or I could write it as P2 V2 ln of V2 over V1. Doesn't matter because temperature is constant across the trajectory. So that's the work done in an isothermal compression trajectory on a PV plot. So now let's do adiabatic compression. So now I'm going to do adiabatic compression. And so again, V1 to V2 of P dV, but P is now V to the minus gamma. So let's say PV to the gamma is equal to K, where K is a constant if we're on a isothermal trajectory. So this will be V1 to V2 of K V to the minus gamma, not infinity, V to the minus gamma dV. And I just need to integrate this, K V to the minus gamma plus 1 over 1 minus gamma. And then this is from V1 to V2, so just do the integral. And this, with a little bit of manipulation, you can show that this is the same thing as 1 minus gamma times P2 V2 minus P1 V1. So adiabatic compression means no heat, right? So the total energy change is equal to the total work done. So we just computed the total work, but we could take P1 and V1 and compute T1, or we could figure out what the temperature is at the beginning, and we can take P2, V2 and figure out what T2 is. And then using those two things, we can figure out what the change in energy is. And so I've done that in lecture notes, and not surprisingly, you get the same thing back. So our assumption that it's adiabatic is consistent with that whole assumption. Adiabatic means no heat. That means the work is equal to the change in energy. So we could have done this, instead of integrating it up like this, we could have actually just said, what's the change in energy? But you have to, the energy, you have to turn, gamma is related to the degrees of freedom. So the mean energy for a monatomic gas is 3/2 kT, which gives gamma 5/3. But if gamma is something else, then you get a different, you get a different factor for the energy. And in fact, you have to turn gamma into n, where n is the degrees of freedom, actually. So, in fact, n over 2 is equal to 1 over gamma minus 1, actually. And so that's where you can see this is giving you the change in energy. So. Okay, so I have a important bit of the, there it is. Okay, out of order piece of thing to do next. Okay, so I keep talking about heat engines. So the second to last thing to talk about now is heat engines. So heat engines, and engines. So we've got some reservoir at a high temperature, and you have some reservoir at a low temperature, and I put my engine here, and there's a heat flow, QH, and there's a heat flow, QL. So my engine, I'm going to take heat from the hot reservoir, I'm going to dump it in the cold reservoir, and as part of that, the whole change in heat is going to give me work. And so out comes a work W is equal to QH minus QL. So the idea is the engine is going around in a loop, so its total energy at the beginning and the end of a cycle is going to be 0, and so the heat change, total heat is equal to the work. And so if I'm taking heat from a hot reservoir and I'm giving up heat from the low reservoir, the total work has to be the difference between them. So this is another way of thinking about what a heat engine is, actually. So with the whole thing, you get work out because you're letting heat be transferred between the hot and the cold reservoir. So what's an air conditioner? Yeah, so an air conditioner is kind of the opposite way. You're doing work and you're trying to make the heat go in the opposite direction. So you're taking heat out of the cold region and trying to make it colder and putting heat into the hot reservoir. So you're going that way so that you're doing work to make the thing go that way. So an air conditioner is like your room is here and you're trying to make heat go that way by dumping heat outside by doing work. And a refrigerator is the same thing, except this is the inside of the refrigerator. And a heat pump is when you're trying to heat your house. So you're doing work and you're trying to heat the hot thing from something cold. So that would be, so you just reverse the arrows for these things, depends. And refrigerators, you're sucking heat out of this. For heat pumps, you're putting heat here. So does everybody make, does that make sense why all of these things are basically the same kind of idea? There's heat being related to work with the engine in the middle, which is doing these cyclic operations. So let's, but it's handy to think about, to come up with a quantity. So remember I was saying, because heat's involved, that means entropy is changing. And so that there's this heat's going to be equal to the work, total heat changes work. So there's a fundamental limits based on the idea that total entropy can never go down. Total entropy has to go up always. So this would put a limit. There'll be a limit on ratios of these things based on entropy considerations. So what do we mean by efficiency of a heat engine? So let's talk about a heat engine. So let's see, efficiency. I want to talk about efficiency. So with a heat engine, you're getting work and you're doing a transfer of heat. And so the engine absorbs QH. And so, and this is at TH. This is the temperature of the hot reservoir. And it's emitting QL at TL. And you're getting W, which is the work. So, so the efficiency is defined by how much work you get by how much heat you're absorbing, QH. So this is a way of saying benefit over cost. So, right, so we can, so since the engine goes around in a loop, that means the total heat is the same as, the heat difference is the same as the work. So I can write QH is equal to QL plus W. And so I can put in, replace this. So that means epsilon is equal to QH minus QL over QH. Like this. Which you can write as 1 minus QL over QH. Okay, so right. So then now this is where we get into an entropy argument. So let's write this up here: 1 minus QL over QH. So So this is where we have to remember that Q is equal to TdS. Okay, right? So heat is temperature times change in entropy. And the entropy emitted by so entropy emitted is QL over TL, and the entropy absorbed is QH over TH. And the entropy of the engine can't decrease over time. So you have to have the entropy absorbed minus the entropy emitted has to always go up. And so that means TQL over TL has to be greater than QH over TH. Because you always have to have more entropy coming in than going out, because if the entropy left the engine after a while, we're going to have zero entropy, which would never make any sense. So you have to have it either stay the same or increase over time. So this is a limit for the engine itself. And so if I take one, so this is looking like this, so I need to take 1 minus this. So let's do 1 minus this. Oh, actually, yeah, let's do, no, what I really want to do is invert this, actually. So let's invert this. So we take QL over QL, not invert it, I just want to rewrite it in terms of Q's. QL over QH has to be greater than or equal to TL over TH, right? And that's looking like this. So now I need to minus 1 from both sides of this thing. So I'm going to do a 1 minus and a 1 minus here, and I have to flip the less than sign like this. And now this looks like that, and this is 1 minus TL over TH. And so the end result is that the efficiency must be less than or equal 1 minus the ratio of temperatures. And this is, so if it's equal, that's the best it can do. And if TL is low and TH is high, you can get closer to 1. And so you can get a more efficient engine. So high T contrasts gives you higher efficiency. Which I guess isn't really necessarily a surprise. This is a maximum limit. So you can say, well, what's the best you could possibly do? Well, the best you can possibly do is if you have an engine that every operation is very carefully designed to be, reversible, and so there's no extra entropy increase happening. And so the worst efficiency you get for the heat engine comes from when you have operations where entropy is increased irreversibly. So the best possible engines would be the most smoothly varying ones. So right. So you could try and design your engine to have the maximum possible efficiency. And so theoretically, so there's these theoretical models. One of them is called the Carnot cycle, which involves 4 trajectories on one of those PV plots. You could also put it in a TS space, and that, if all the operations are nice and reversible, that actually achieves this maximum efficiency. So if we have time, which I'm not sure we do, we'll look at the Carnot cycle. Okay, so what I want to do now is I have a few minutes left for lecture, so I wanted to show you what, well, I suppose we're not actually out of time. So any questions on this thermodynamic stuff? See, people are kind of paying attention. Questions? No. Yes, maybe? Okay, so I'm going to share my screen. So the thing I want to share is this software called Audacity, which is recording software. It's free, open source. So this is what I'm recommending you guys do for the lab. And I have this ball, so you can bounce it. So I thought I'd just show you how to play around with Audacity. So this thing, you know, you can press this red button and you record. Hello, there's my voice. Bounce the ball. Okay. So that's the recording. So I tested this right before lecture. So hopefully you guys can hear it. So if you press this green thing, bounce the ball. Can you hear that? Yes, I hear it. Yes, good. So so that's what you're supposed to do for lab number 5. But we could take a look at this. So what do I want? So that's record, that's stop, or that's play, that's stop. This is pause. Here, I think I'm recording on mono. You can see this is my microphone. I guess I could record off of the Zoom. These are which speakers it's going to. Important things. So my project rate, that's the sampling rate. So what it's actually doing is it's taking a digital number for every sample, and the sampling rate tells you how fast that's happening, and the time between samples is 1 over that. So 1 over 44K gives you the time between audio samples. And here you can see if I'm choosing a particular region, it's giving me the start and end of selection. And this is in hours, minutes, seconds to 3 decimal places. And I think you can set that with pull down menus. So this, without doing anything fancy, you can measure time to a millisecond. I mean, you could do better than this if you want to actually count individual samples. So here at the bottom, you can see this will let you give time in various different ways. Hundredths, I think I put it in hours, minutes, seconds, plus milliseconds, just because a millisecond is pretty good for this experiment. So, but it's nice to actually be able to zoom in here. So this button just lets you zoom in. So, and then you can move around. So if I want to see, this is a particular bounce, I can zoom in. I can also go like this. And then I think if I do that, it will let me expand the whole region. So now you're starting to actually see what the sound file looks like on short times. And probably right around there, if I choose a region like this, that is a pretty good estimate for the onset of the bounce. You can look, well, why do you hear, why is the sound doing all of this? So this is echoes. It's called reverb, and your brain actually turns off reverb. If you turn the sound file backwards and played it backwards, it would sound like zoop. And so you don't really notice that your brain is removing echoes, but that's because we live in an environment where echoes are all over the place. So it's not just echoes. When the ball hits the floor, there's actually sound waves going through the floor, and they're faster than sound going through the air. So some of the sound is radiated from the surface of the floor too. But in any case, that's all what that is. So what we're trying to do is measure the time between bounces, right? So you could worry about things like, is the sound travel time different? So when I dropped that ball, it was actually bouncing, or moving further away from my microphone, which means if the bounce onset is coming from slightly different distances, so you could worry about that. And it would make some difference, actually. So those are things that you can think about when you're writing your lab report. But mainly, all you need to do is go and measure the times. So here, this would be like in milliseconds. Measure the times, and like all our labs, you have to estimate, well, how well do I know that number? And so here I just said, well, maybe I know it to the width of that window, and it's telling, here I have start and end of selection as possible ways to measure the time. So any case, so that's mainly what you want to do is bounce the ball a few times. And I did a rubber ball, but you can do this with things that are hard too. And I bounced it on a wood floor. It's actually kind of bouncy. So those are other issues that you might think about in the affecting your measurements. Is what surface are things moving? Is it spinning? Is the air resistance important? So there's a lot of factors that could be affecting your measurement and your estimates for the coefficient of restitution. So coefficient of restitution is just when something hits the velocity. So if it were perfectly elastic and the ground were perfectly elastic and not moving, the velocity down would be the same as the velocity up. So the coefficient of, and there's no energy loss, the coefficient of restitution would be 1. How are we going to get the coefficient of restitution? So we're measuring the time between the bounces, but if it's a parabolic trajectory, you can figure out the velocity, initial velocity from the time between bounces. And so you need a bunch of bounces to get velocity changes between the bounces. So you need to get a single velocity, you need to have 2 times. So if it bounces once, twice, that gives you a single velocity. If you measure 3, you get 3 times, you get 2 velocities. Measure 4 bounces, you get 3 velocities. And that's enough to see if you have a change in the ratio of velocity in before and after between consecutive bounces. If you do a rubber ball, you can probably get 10 bounces easily before it hits the wall or something. If you do a marble, I found I could get, I don't know, 4 or 5 bounces. If it's not round, then of course it's going to change direction. So I'm kind of it's probably better if you do this experiment with things that are round. Otherwise, there's things like rotations, and it winds up going off in weird directions eventually. Yeah, so that's mainly what I wanted to show you guys, and with the software. Any questions about the 5th lab? So Monday, you guys will be meeting either online workshops or on-campus workshops remotely just to talk about the 5th lab. But that's basically what you're doing. And on Tuesday, I'll talk about order of magnitude estimates for that lab. But any questions? Well, while you guys are thinking of questions, we have a few more minutes, so I guess we can talk about the Carnot cycle.
So what exactly is happening on Monday with the people, like on Zoom?
Right, so Kai and Angel and Viv are supposed to be emailing you at some point to say that you guys are going to meet online to talk about the lab. But so take a look at the lab manual. What I recommend is you get whichever, so if there are 2 ways to do the lab. If you're online, you could use the IO lab devices because they have a microphone in it, and the IO lab device software, which is also an open source thing. If you have an audio file from the IO lab device, you can measure onset the times of those bounces using that. So the online group probably will be using the IO lab device, and you can share the sound files. So the other group, the on-campus group, I'm encouraging you to go get Audacity, which is an open source version of what used to be called Adobe. That's why I keep slipping. Go get Audacity, put it on your computer, and play around with it. So and you also need to find something round. If you're really stuck, find a friend who has something round and get them that. I showed you how you get a sound file, but Audacity will let you save it. You can email a sound file to one of your friends. So not everybody not everybody needs a rubber ball or a marble or a tennis ball. It could be anything round, right? So you can share the files and then read them in either platform. But what I recommend is for Monday, so there should be at least 3 sessions, 2 on-campus sessions run by the TAs for your on-campus labs, or an on-campus one that Ryan's running. Be ready to take data for your labs so you can talk about it.
So we will take data on Monday while the TAs are there.
Yeah, and then that way you can ask them, well, what should I do? But look at the lab manual. So I did send the link. The link is on the website in the labs. It's also linked through the Blackboard. So make sure you have the lab manual. So it's part of the online lab manual, the last chapter, to see what's asked of you. But I basically told you what's asked. You measure the times between the bounces, measure the coefficient of restitution, and then talk about it. And one of the questions in the labs is, do you feel like the coefficient of restitution is actually a constant? It may not be a constant. Does it depend on the velocity? So, and your data may or may not support dependence on the velocity. So, it's like all the other labs. You have to think about how well can I measure it, and how well, is it significant if I'm seeing a variation between it being fixed or not, or being a constant or not. Does that help answer your question?
Yes, thank you.
Yeah. So so that's Monday, which is before the end of classes, right? So the end of classes is on Wednesday. So the TAs and TIs are kind of around next week, but then they're going to be like you guys, busy with exams afterwards. So even though the final lab is due on the 16th, which is another, what is it? That's like 12 days from now. I encourage you to get started on it Monday, because the TIs and the TAs are there to help you next week. But as soon as classes end, they are not around to help you. So that's another reason. I'm still around to help you, but the TIs and TAs are not around to help you. So that's the reason. If you're going to do the last lab, which should be kind of fun, then get on it on Monday. Do you see the point here? Yeah. Okay. That's the other reason. Any other questions on the lab? Do we have time? I guess I have a few minutes to talk about the Carnot cycle, but if there's another question, interrupt. Oh, we do have a question. What happens to the adiabatic index if you have a mixture of two gases? Oh yeah, so you probably have some combination. So the question is, what if I have a mixture of a monotonic and a diatonic gas? Then you want to compute the average energy for the whole thing, and then N would be something intermediate. So we did that derivation. There were two things I needed: the ideal gas law doesn't care about the adiabatic index, and the mean energy, which has the degrees of freedom in it. So those are all that you need. And so if you adjust that N/2 factor to take into account the ratio of the two gases, you can come up with an adiabatic index that would be correct for that mixture. So I think, so this is ideally it's possible. This wouldn't necessarily tell you about things like, so these are ideal gases, they don't interact. So there are other things going on. You can also have dissociation, you have radiation. I mean, there are a lot of things that make things not ideal in gas setting, but that you could definitely rederive with a mixture of gases. Any other questions? Actually, that was a pretty good question. And that Ellie gave that question. Good question. Okay, well, in the last few minutes of this lecture, what's a Carnot cycle? And why is it important or famous? So I gave you this really rough feeling for what the efficiency of a heat engine is, but people like Carnot and his theoretical model of the perfect engine were the people who established this was a fundamental thermodynamic limit for heat engines and air conditioners and heat pumps, all of those things. So that's why it's important. I think before that, people were like, why can't you get infinite amount of work out of a small heat transfer? So it's actually a fundamental thermodynamic limit based on entropy considerations. So these toy models like the Carnot cycle established this, probably correct. It is correct. So what is a Carnot cycle? So yeah, it's this 4-step thing. And So let's do the steps. First, you have to start with a hot reservoir. So it's hot. That's the hot TH. And that's going to be step 1. So I have my little, and then I have a cold reservoir. Oh, this thing's dead. Blue. I have one out of blue. That's very sad. I don't think I have another blue. All right. Cold reservoir. TL. And then we're going to have, so let's put our little gas thingy in here. Piston. And I'm going to put sand on it. Okay, so here's the sand pile. So this is step 1. Step 1, and it expands from V1 to V2, and it's in the thermal reservoir, so it expands isothermally at the higher temperature. So that's step 1. So step 2 is over here, and now it's isolated, and yeah, so we're taking off, actually, we're taking off sand because we're letting it expand. So, actually, no, we don't have to take off sand. What I really mean is we're putting it in the bath and it's heating up, and that's what's causing it to expand. So temperature causes it to expand. Step 2, that's when we take the sand off. So we're taking off sand, and now it's isolated, and it expands from V2 to V3, but this is adiabatic. So this is an isothermal expansion, that's an adiabatic expansion. This one, we're not changing the weight on it. This one we are changing the weight on it. Both of these are changing volumes, so there's work going on. This one we have temperature change. And that one you don't have any heat because, in this one you have heat flow because there's heat flow in this direction because the gas has to heat up. In this one there's no heat flow because it's adiabatic. So go that way. Now we have step 3. So step 3, we've taken off the sand, so we have a little bit of sand, and now we're putting it in the cold reservoir, and so it's going to cool off. So it compresses now. Compresses from V3 to V4. And this is isothermal, so it's not isothermally, but it's in the bath. So it's maybe not isothermally, but it's going to get to TH. So it goes to TL. And then this last step reverses, because there's no bath, it's isolated. So now we didn't have very much sand on it, so we have to put sand back to reach the beginning state. Add sand, and now it goes back to V1, V4 to V1, and so it's compressing, and it's adiabatic. Adiabatically. There. So this is step 4. Step 4. Step 3. So those are the 4 steps of the Carnot cycle. And so we can now look at what they look like on the PV plot, actually. And so what's this look like in the PV plot? So V and P, and so it looks something like this, and then it goes this way, and then it goes like that, and and this is at V1, and this is V2, this is V3, and that's V4. And this one, so this is volume increasing, so this one is step 1. And this one is at TH. So this is on an isothermal curve. This was TL, that's step 3. This is step 3. And that's on an isothermal curve. These two, this is step 2. That's on an adiabatic curve. And this step 4 is also adiabatic. So the point of doing these alternating isothermal and adiabatic operations is that you can easily calculate what's going on this plot, because we have a formula for how things vary if they're adiabatically, and we have a formula for the work done if things are varying isothermally. And so, so we did all these previous part of this lecture, we calculated what's the work if it's adiabatic, or what if it's an adiabatic trajectory, what's the work if it's isothermal. And so we can calculate the total work done around the loop, and that has to be the total heat done on the loop. And that lets you calculate the efficiency. So this is what it looks like on a PV plot. On a TS plot, when it's adiabatic, S is not changing. When it's isothermal, T is not changing. So on a TS plot, so if I have S versus T, the loop looks like a square. And it makes it with the same area, actually, because the total heat done around the loop is the same as the total work on the loop is the same as the total heat on the loop. So when you get back to the beginning, you have the same energy. But the operations here let you compute the heat transfer on from the hot reservoir, and lets you compute the total work. And then you can take the ratio of those. And when you do that, you actually get the ideal efficiency, the maximum possible efficiency for a heat engine. And so this little experiment shows you that limit makes sense. At least it's a theoretical limit, because real heat engines don't actually achieve the maximum possible efficiency. Okay, so what happened in step 4? Step 4, it's isolated, so it's adiabatic, so there's no reservoir, and we're letting the temperature, the volume is going down, so it's a adiabatic compressive step. So we're adding sand to get back to the initial condition. So that's what step 4 is. So these are isothermal. This is in the cold bath, that's in the hot bath. These two are isolated, where they're adding sand or taking away sand. This one we're adding sand, that one we're taking away sand. And you just figure out whether you're compressing or letting it expand, to which one is which. In any case, that's it. That's the Carnot cycle. Yeah. And actually in the notes, I do actually go through the calculation, but it's pretty much, yeah, so you just have to if you integrate the work, it's the same thing as integrating the heat. And that lets you compute the, so if you know QH, which is the heat transfer that happens on this step, and so you integrate the whole work and you divide by QH, that gives you the efficiency. And so you could show that, in fact, it is equal to the maximum efficiency possible. But I think I'm kind of out of time, so I'm out of time. So if you want to look at the actual calculation, so it's not a very long calculation, it's a short calculation. Okay, so that's the end of lecture today. Any more questions? If not, I'll see you guys on Tuesday. Don't be strangers. And have fun with the last lab. And hopefully the problems at problem set shouldn't be giving you too many problems. Somebody did point out an error in units that I fixed it. So last problem set, number 5, had cal meant to be joules, so that's fixed. Thank you for pointing it out. So far, I haven't found any other errors on it, so it should be straightforward, especially based on what I just covered today. So I'll say goodbye, unless there are questions.
Thank you.
Bye.
Thank you.
Thank you.
Thank you.
Bye.